Greetings everyone. Today I'm delighted to present a comprehensive overview of a significant project. This is the prediction of rainfall in Australia, and while this may appear to be straightforward, its implications, particularly in light of such recent events such as the devastating wildfires of the past year, underscore its critical importance. Why is it important? Why does predicting rainfall matter on such a scale? The answer lies in the fact that it has a far-reaching impact, particularly in agriculture sector, where accurate forecasts are indispensable for crop planting and drought mitigation. Furthermore, in the aftermath of wildfires, precise rainfall predictions play an important role in disaster prevention and management, ultimately influencing public safety and environmental well-being. So now we can look into the data set. So this data set had about 26 variables and a ton of data points, but these are some of the most important predictive factors that I wanted to mention. We have rainfall, evaporation, sunshine, minimum and maximum temperature, and even cloud coverage at different times of the day. This data comprises both binary responses, continuous data, and it's a complex data set. And I like to compare the predictive analysis almost to solving a complex puzzle. We're figuring out the intricate relationships that lead to the precipitation. Okay, now we can look at the model. So this is how I designed the model. I did a data retrieval. I began by retrieving the dataset from reliable sources such as the Bureau of Meteorology in Australia. This ensured the integrity and accuracy of the data. Then to prepare the data for modeling, I performed numerical to binomial transformation, converting continuous variables into binary ones. Then I converted that into real data, and then I set the role. I designated rain tomorrow as the label or the target variable, while the other factors became attributes. This step clarified that each role this step clarified the role that each variable plays in our predictive modeling. For the attribute selection, I carefully selected attributes that would contribute meaningfully to the model. Notably and important to this is I eliminated the variable risk MM, which is had a strong effect on the predictive model at the end, upwards of like a 20% difference. So I found that by eliminating it, I could reduce the skew in the model's accuracy. For the data sampling, given the potential imbalance in the data sheet, where instances of yes or no for rain tomorrow might be uneven, I sampled the data to ensure equal representation. I chose in my sample 10,000 data points for yes and 10,000 data points for no. So now let's talk about the cross-validation. This is definitely the most important step in all of the project. So I tried multiple different models. These came from the auto model first as a suggestion, and then I just began experimenting with some of the different models based on those recommendations and based on what I have done in the past. One of the more successful models that I found was the random forest model. Opting for the random forest model introduced a layer of complexity that was essential for capturing intricate relationships within the data set. This is known as an ensemble learning method, and it aggregates predictions from multiple decision trees, which is why it's known as a forest, and it demonstrates a very robust and resilient prediction style. And before I get to the outcomes, I want to go ahead and talk about what I did with some of the other models. So next I chose the naive Bayes, which I chose just because it is a simple and efficient, well-known model, and it's particularly suitable for handling large data sets with numerous predictors. It assumes independence among predictors, which aligns well with this diverse data set of weather variables that influence rainfall. After these models were selected, I went over the following steps that were crucial for evaluating and applying them efficiently. So for the cross validation and the application, once the models were trained and validated, they were applied to real-world scenarios. This step involved using the models to make predictions based on new data. So that is the application that we can see over on the testing side. So the training is going through, and then the testing is actually applying it to new quote-unquote data points, which can provide valuable insights for possible decision-making in agriculture, disaster management, and other similar fields. Now we can go into the results. So even though I tried 4 or 5 different models, I want to just mention 2 to you all. I found that the naive bias and the random forest were the most successful, each at about 75% accuracy. That is a little bit lower than you might see on some predictive modeling, but that's accounted for just because of how complex this data set is. And it is also makes sense because when we think of our ability to predict rain, now it's not always true. You think of maybe like there being a 20% chance of rain tomorrow. Even weather professionals don't know exactly what is going to come. So I found that the random forest model was a better model overall, and I would recommend using it in the future for future predictions, just because it did have a higher accuracy. And when I went through some of the graphs later on that I'm about to show you, I saw that they supported the predictions from this model. Here's one of those graphs. I graphed multiple different data points, but this is just a good example. This shows humidity. And so in the green, we can see yes being yes, there was rain on the next day. So rain tomorrow being yes is the green. So like at a higher humidity, that does in fact impact the yes rain tomorrow variable. And we can see in the blue that would be no. So the lower the humidity is, the less likely there is to be rain tomorrow. And to support my model, being random forest, I also went over several other of these graphs, including temperature, which was kind of surprising how dramatic of a relationship it showed, and several others, but I don't want to spend too much time here, so I won't show you all of those. So now I want to talk a little about implementation. So the whole point of doing this project is to train models into an operational system. This is where we can integrate into stakeholders, including the agriculture and disaster management authorities. Hopefully in the future we could access real-time predictions, which would facilitate proactive decision-making in response to varying rainfall conditions. It can really help with possible flood predictions in the future. As climate change gets scarier, these models become more and more important. And in conclusion, this exploration into rainfall prediction in Australia signifies more than a technical endeavor. It symbolizes a commitment to basically gathering all this data and analyzing it for all of society. As we navigate the complex landscape of weather forecasting and agricultural forecasting, these predictive models offer big insights, and they aid in a strategic planning for all these things I just mentioned. The graphs coupled with model selection and deployment considerations contribute to a greater holistic approach which aims at addressing the fundamental challenge for rainfall in Australia's future. I appreciate your patience in listening to me and joining me during this analysis, and I look forward to continued discussions. Thank you so much.